Hello, in this video we're going to look at the final problem from the 2025 Beijing Gao Kao math exam. Here it is in the original Chinese, so if you would like to pause the video and read the original Chinese, do so now. Otherwise I'll show the English in a minute. First I'd just like to thank the person who recommended this problem about a funny board game, so let's take a look. So we have A as the integers from 1 to 8, and M is a set of coordinate points where X is from 1 to 8, Y is from 1 to 8. From N, we're going to select N elements to form a sequence. So this is going to be a sequence of coordinate points. And the conditions for this sequence of coordinates must be that the adjacent terms must satisfy either the difference between the X coordinates is 3 and the difference between the Y coordinates is 4, or the other way around, the difference between the X coordinates is 4 and the difference between the Y coordinates is 3. If so, this is called a K sequence. So to understand this, we probably want to draw up a diagram. And we can start just by jumping into the first part of the problem, which is if the first term of a K sequence is 3, 3, find the second term. I've drawn up an XY grid there from 1 to 8 and labeled 3, 3. So where could we go next? We either go 3 steps across and 4 steps up, or 4 steps across and 3 steps up. We have to land on an integer from 1 to 8. So that gives us two choices. Either we land on 6, 7 or 7, 6. So the first part of the question there is just really testing our understanding of the problem statement. Problem 2 is where things get a little bit more interesting. Let tau be a K sequence such that when I is odd, Xi is in 1, 2, 7, 8. When I is even, Xi is in 3, 4, 5 or 6. Determine whether 3, 2 and 4, 4 can both appear in tau and explain your reasoning. I'll also show part 3 here, prove that all elements in M cannot form a K sequence. So if you want to pause the video and have a go at the whole problem yourself, feel free to do that now. When I read this problem, it reminded me of the Knight's Tour problem, which is where a chess knight has to visit each square on the chessboard exactly once. The only difference is the chess knight moves 1 step across and 2 up, or 2 across and 1 up, whereas we're going 3 and 4. So here's part 2, and I think it helps to again draw a nice diagram with some color. So if we label the region on the board where X is in 1, 2, 7, 8 as blue, they're going to be the odd terms in our sequence, and the even terms are going to be in 3, 4, 5, 6. We'll label that as pink. We want to determine whether 3, 2 and 4, 4 can both appear in our sequence. And noticing they're both in the even term, so in the pink region. If we start from 3, 2 and try to make a sequence that joins to 4, 4, from 3, 2 we can go to 7, 5, from 7, 5 we can go back to 3, 8, but then we're kind of stuck, so try something else. We can go back to 4, 1, keep going. What we start to notice is a pattern in the positions of the blue and red points. They always seem to be lying on alternating diagonals. And it is always going to be the case. Where we can prove that is by looking at the sum of the X and Y coordinates. Each time we make a move, we either add or subtract 4 and add or subtract 3. In either case, an odd sum is going to go to an even and an even sum is going to go to an odd. So the sequence of terms is always going to go odd, even, odd, even, odd, even. 3, 2 has an odd sum and 4, 4 has an even sum. So they cannot both be terms when I is even. Similar to how, in the traditional Knight's Tour, the knight always jumps black, white, black, white, black, white. So here's part 3, prove that all elements in M cannot form a K sequence. This bit obviously is the most challenging part. My first attempt was to start from the point 1, 1 and just see like where can I go and why can I not travel to all the points. So I did that for a while, but actually I could get quite far, like a lot further than this, and I wasn't too sure how to prove why I couldn't just keep going and fill up the whole board. So I tried another approach, which was to think about like, what are the maximum possible choices you have from each point on the board? If we're not limited to the integers from 1 to 8, actually we would have 8 choices. 8 choices for the next move. But because we are limited to only integers from 1 to 8, even from this square here at 5, 5, these 4 points are all taking me off the board. So I only have 4 choices left. And that is going to be the most possible choices I have from any point on the 8 by 8 grid. If we were to go back closer to the corner, like from this light blue point here, I'd only have 2 choices for where I can move. And the other points where I'd only have 2 choices are going to be anything where the x coordinate and y coordinate are both 3 or less, because I can't go left down to 0 or down to 0 or into the negatives. So from all these points here, I'm only going to have 2 choices for my next term in the sequence or my previous term in the sequence. The 4 terms in the middle is where I'm going to have 4 choices. And then for the leftover points, you're going to have 3 choices from all of those points for your next or previous term. And notice none of the orange points link up to the red ones. So my approach was to take one of the orange points and link it up to the 3 blue ones that it could connect to in the sequence. But then the thing is, each term in a sequence can only have 1 term before and 1 term after. So it can't link to 3 different terms, which means one of those terms is going to be left out. Because that term only had 2 that it could connect to originally, one of them is gone. It only leaves 1 more point that light blue term can connect to, and that means the sequence must end there. In that example, the sequence must end at 7, 1, because there's only one other point that it can connect to, which is 4, 5. So just to write that out a little bit more clearly, point 3, 4 can only be adjacent to 2 out of the 3 points, 6, 8, 7, 7, and 7, 1. And each of those points only have one other point which they can be adjacent to. So the one that's not connected to 3, 4 must then occur at the end of the sequence. But that's a problem because we can only have 2 terms at the very end of the sequence. And we can essentially do that same trick, repeat the same trick from the points 4, 6 and 6, 5. It's going to give us 2 more points that must also occur at the end of the sequence. That's a total of 3, and a sequence can only have 2 endpoints. Therefore, the sequence is not possible. So after having come up with that argument, I still felt like maybe there was a simpler solution I was missing, because generally with the way these problems are structured, what we've done in part 2 is going to help us to solve part 3. And for me, I thought maybe there was a closer link that I was missing. So I found a solution online, and this is how it works. If we consider the 16 terms whose x coordinates and y coordinates are in 1, 2, 7, 8, we get these 16 points, like 4 in each corner there. Each of these 16 terms can only be adjacent to the 12 terms with x and y in 3, 4, 5, 6, but not 3, 3, 3, 6, 6, 3, or 6, 6. Because from 3, 3, for example, we're going to have to add 3 to one of those coordinates, and then we're not going to get up to 7, so we're not going to get to one of those blue points. Now, we have 16 blue points that need to alternate with only 12 red points in a subsequence. That cannot exist, so therefore all elements in M cannot form a K sequence. So that solution is probably nicer and cleaner than my original one. It is a nice problem, I thought. Really helps to have a nice clear diagram. It probably also helps to have, if you'd seen the original Knight's Tour problem before. If you have any alternative solutions or comments, feel free to leave that below. Otherwise, I'll end it here. Thank you.